This tutorial is about parametricity properties of purely functional code. Some of these properties are known under the name theorems for free. I will show other properties, and I will also show that the theorems are not actually for free. There's a price to be paid, and the price is that all your code must be purely functional. I begin by saying that there are actually 4 results that I call parametricity properties. And these properties are related to something called naturality laws. So what are these 4 results? The first one is sometimes called the parametricity theorem. It is a statement that purely functional programs will automatically obey a certain law or a set of laws called the naturality laws. Now, these programs must have a type parameter, or at least one, maybe several, and they must be of a function type, such as this example. The standard method head option in Scala has this type signature. It's a function from a list to an option, and it's parameterized by a type parameter a. It satisfies the law, which can be written in the Scala syntax like this, or in the code notation like this. Now, the code notation is something I developed in my tutorials on functional programming, and I'm using it also in the book that I'm writing. So, just for people not familiar with the code notation, the up arrow means lifting of a function f to a functor list, and this is a lifting to the functor option, and the semicolon means composition of functions, but it's the forward composition. First you apply this function, and then you apply that function. So in the Scala syntax, this composition is naturally written as a chain of methods. Dot map of f is this, and dot head option is this. So in this formula, I'm not writing the argument of these functions, but in the Scala code, I usually would write that argument. So this is an example of a naturality law, which is specific to the type signature of head option. And for all other functions that have naturality law, it will have a slightly different form. So the form of the naturality law depends on the type signature of the function. So actually, while parametricity theorem says that programs will automatically obey that law, there still remains the question of how to write that law for a specific type signature. So that is the second parametricity result, as I call it, which is that given a function's type signature, there is a recipe for writing the naturality law. And this recipe is based on the techniques that are called dinatural transformations and profunctors. So I will explain in this tutorial what these are. But given that we have a transformation with this type signature, we always have a naturality law which is written like this. So this naturality law is general. It holds by parametricity theorem. And for any specific P and Q, you can derive a specific form of this law by substituting the code of the method xmap for p and for q. I would like to note that in the code notation, the lifting always says to which functor or contrafunctor or profunctor the function is being lifted. Whereas in the code, this is not shown explicitly. It is left implicitly determined from the type of the list. So if you know that this is of type list, then you know that this dot map is the lifting related to lists. But here, this dot map is related to option, because you know that head option produces a value of an option type. But the notation in the Scala code does not show that. So the code notation shows that more explicitly. And I found that to be useful. So the code notation mostly is useful for computations by hand. And it is optimized for that purpose. So this is now the second result. The third result is the commutativity law for profunctors and bifunctors. So an example of a bifunctor is the IO type constructor from the ZO library. But it doesn't have to be so complicated as IO. It can be any type constructor that has two type parameters, and it is covariant in both of these type parameters. So it's covariant in each of them separately. So then you can have a dot map method that applies to one of these type parameters, and another dot map method that applies to another, to the other type parameter. For the IO type constructor, these methods have different names, map and map error. And this is because the type parameter E is intended as the error type, and the type parameter A is intended as the result type, the successful result type. So that's why these names are chosen like that. But in any case, the commutativity law says that you can map over one type parameter and then over another type parameter in any order. So if you swap the order, the composition remains the same. That is the commutativity law. And there is a similar one for profunctors, which I will show later. So the third parametricity result is that if a type constructor is implemented with purely functional code, then it should satisfy, it will always satisfy the commutativity law. Now, certainly the IO type constructor in the ZO library is not implemented with purely functional code. But nevertheless, I would expect it to satisfy this law. This law is an important law that I will not derive why this law is important, but I will just indicate the reason. The reason is that if you have a type constructor that has two type parameters or more, and it is a functor separately with respect to each of these type parameters, then you can define a method called bimap that maps the two type parameters at once. And this method will then satisfy composition law. And this is not true if the commutativity does not hold. So I will discuss this later. And finally, the fourth result is that functors and contrafunctors are uniquely derived from the types of the type constructors. So for example, consider this type constructor in the Scala syntax. It's covariant in the type parameter A. And the functor instance means that we need to define the fmap function with this type signature. And here's the code for it. So this code is purely functional, and this code is unique. There's only one such code. There's nothing else you can do to implement this function while obeying the laws of fmap. So, for example, here you have the case left. You must return a left. There's no way that you could here return a right. Although you could write code, for example, that takes a left here. You have a value of type A, and then instead of this you return a right of a function that ignores its string and always returns this A that you had here. This would satisfy the type signature, but this would not satisfy the laws. Or here you could say I have a right of g, so g is this function, and I need to return an either of a int. But let's return the left. Instead of int, I'll just use the number 100, and instead of a, I will call this function g on a string value, and the string would be, for example, abcd. I'll just hard code the integer 100, the string abcd, and I will satisfy the type signature of the fmap, but I will not satisfy the laws. So this is a result that can be proved, that as long as the function fmap satisfies the laws, there's only one implementation. I mean, I can change the code equivalently. I can, for example, introduce an identity function somewhere. Instead of n, I write identity of n. Well, this is silly. It doesn't do anything. It just makes the code superficially different. So if I don't do that, or I say modulo all equivalences and such superficial differences, there's only one code. So that is the fourth result. Now these results are important for practice, as I will also discuss. And these are the parametricity properties which follow as long as your programs are purely functional. So what does it mean that your programs are purely functional? It means you are using only the 9 constructions of code that I'm listing right here. So it's very interesting that the functional programming paradigm tells you that you can use only the 9 code constructions. So you can list them and you can say, this is the functional programming paradigm, writing code using these constructions. Here's an example. So I implement the fmap function for the type constructor of list of pair AA. So I map list of AA into list of BB. How do I write this code? Well, this code is unique in terms of purely functional code. There's only one way of implementing this, up to equivalence. And it is like this. So if I do pattern matching on the list, if it's empty, I return empty. And if it's not empty, I have a head and a tail. A head must be a pair of A and A, so I extract values from this pair, apply F to those values, I get a pair of values of type B, and I append the recursive call of fmap on the tail. Now, I have written here in comments which constructions are being used in every place. So what are these 9 constructions? Use unit value, use the bound variable, which is a given argument of the function, create a function, use a function, which means to apply that function to some argument, create a tuple, which means you already must have A and B previously computed, so you make a tuple out of them. Use a tuple, for example, take 1, the first element, part of the tuple, or the second one. Create a disjunctive value, or a value of a disjunctive type, such as a left of either or right of either. Use disjunctive value, which is pattern matching. And finally, use recursive call, so you can call the same function within its definition. And here are the usages. So here I create a function. I use the unit value. Now notice that nil is actually a unit value which has a name. It's what I call a named unit. Another example of a named unit is none. Here I create a value of the type list, which is a disjunctive type, using the named unit. So I use number 7 to create disjunctive value and number 1. Here I have the case construction, which is number 8, head and tail, which is number 6. I'm using parts of the tuple because the list constructor colon is a tuple of 2, is a pair. So this deconstructs the tuple. So this is another syntax for deconstructing the tuple. Here I'm creating a tuple, which is number 5, out of result of applying a given function, construction 2, to a, I'm using the function construction 2, and I'm applying it, construction 4. Construction 6 takes part of a tuple, construction 5 creates a new tuple, and so on. And here finally I have construction 9. I'm using the same function in its definition, which is a recursive call. So in this example, all 9 constructions are used. So this is what purely functional programs must be. They must be some kind of combination of different code constructions. So parametricity theorem says that any purely functional program must satisfy naturality law. But what is a naturality law? Why is it interesting? Turns out that a naturality law is a mathematical formula or equation that expresses the intuition of programmers about the properties of code, which is written in a purely functional paradigm, and it becomes fully parametric if it has a type parameter. In other words, the code is written only once, it has a type parameter, but it's the same code that works with all types. So the code is such that it works in the same way for all types. For example, the implementation of head option has a type parameter A, but it works exactly in the same way for all types A. So this is what I call fully parametric code, and it has these properties that, for instance, all argument types must be some combinations of type parameters, and all type parameters are treated as unknown and arbitrary types. So there are no hard-coded values of these types since they're unknown, and there are also no hard-coded values of any specific types, such as 123, which would be an integer, or ABC, which would be a string. So we are not using any of that in the fully parametric code. Now, purely functional code, in principle, would allow us to do that, but fully parametric code does not. So naturality law enforces full parametricity, and purely functional code actually does not include constants like 123 or string ABC. It only includes the 9 constructions here. So if I think about a code like this, for a type like this, then I must treat arguments of types integer and string as if they are of absolutely unknown types, as if integer and string are some other type parameters. So if you look at this code, this is what it does. It does not actually use the fact that n is integer. Using that fact would be, for instance, saying here n plus 1 instead of n. Now that you can write, and it will be admissible in Scala, but it would not be fully parametric, and it will not be purely functional. In purely functional code, there is no plus. So that's why there's this restriction. So actually, like I said, theorems for free are not for free. It's a misleading name. There is a price to pay. The price is that you must write fully parametric code using purely functional type constructions, code constructions. Sorry. So no side effects. There are no ways to express side effects in these constructions. So for instance, you cannot print anything. You cannot have a variable that you reassign. You cannot write a file. You cannot download something. There are no side effects. There's no null. Now null is the Java compatibility value, which Scala code usually does not involve unless you're working with Java. There's no throwing of exceptions. There's no detection of type at runtime and comparing types at runtime. And you can write code in Scala that, for instance, determines whether a is actually integer when this function is called, or string or some other type, and do something in that case. Now that is not one of the constructions, so that is not allowed in a purely functional code. Now, actually, I should clarify that fully parametric is a consequence of being purely functional. So all these properties are consequences of the code being purely functional, consequences of restricting the code to these 9 constructions. So there's no loading code at runtime, there are no external libraries that you can call with some unknown code, which might not be purely functional, so you're not allowed to call external libraries. So that is the price you have to pay for supposedly free theorems. So how to formulate a naturality law for a function, let's call it a transformation, t. Now, a transformation is because it must be of a function type. So naturality law is an equation that involves an arbitrary function f And the equation permutes the order of application of t and lifted f. So as we just saw in that example, there was a lifted f, and then you apply the transformation t, so t is head option in this example. Then you do the same in the other order. You first apply the transformation and then the lifted f. So the intuition is that the function f, this must be t, function t, not f. This is a mistake. The function t somehow rearranges the data in a collection and prepares another collection out of the first one. And this rearrangement does not depend on the type of values in the collection. So this rearrangement is done in the same way for all types. For example, taking the first element of a list, this is done in the same way regardless of the type of the values in the list. So now if you transform the values in the list in some way using a function f, you get different values of type b, which could be a different type. But transforming before rearrangement will be equal to transforming after rearrangement, because the rearrangement does not know about the types. So it will work in exactly the same way before transforming a list and after transforming the list. So that is the intuition. And the code that is written once for all types A must satisfy this property, because then it works in the same way for all types A. So that is the intuition behind fully parametric code that treats all values as if they were of some unknown type A. More examples of naturality law. For instance, the transformation is a reversing of list, and reversing the order works in the same way regardless of the type. So then there's this law. You can first transform the list and then reverse, or you first reverse and then transform, and the results are the same. Well, this is quite clear. For example, if your transformation, imagine that you have a list of integers and you transform them by multiplying each integer by 4. Now, if you reverse it, then you get multiplied everything by 4 in reverse order. So you can first multiply by 4, then reverse, or you can first reverse, then multiply by 4. It's the same result. And another example is the pure method, which takes a value of type A and produces a value of some type constructor L of A. Let's say L could be list or option or something like that. So if a type constructor L has such a method, it's called pointed type constructor. So this is the code notation for this function that I'm using. This is again a mistake. This should be L, not F. I will change this after the recording. So the naturality law is that you can first apply a transformation and then apply pure to the result, or you can first apply pure and then apply a lifted transformation. And in the code notation, this is written like that. So the naturality law interchanges the order of application of the function, that is the transformation t, which is here the pure, and a lifted arbitrary function f. So this law is holding for arbitrary functions f of arbitrary types a to b. And you see The form of this law is slightly different because there is no lifting on this side, but there is actually a lifting in a trivial sense, as we will see. So why is it important to know about naturality laws? Mostly this is important when you are reasoning about other laws, such as different laws for type classes. So type classes, for example, functor, filterable, foldable, or monad, they involve type constructors with certain methods, such as map, filter, fold, and flat map. But these methods are not just accidentally chosen functions with some type signatures. These methods must satisfy certain laws in order to be useful for programming. These type classes were discovered out of programming use cases. What are those laws? Now, I'm not going to write them out. It's quite a lot of equations. But there are different laws, and most type classes include naturality laws. So when you implement a new type class instance, you should check the laws. Otherwise, you're not implementing the type class correctly. So the parametricity theorem guarantees that naturality laws hold as long as the code of your method is purely functional. So for example, if you're implementing flat map for some data type, you should check identity law and laws. There are two identity laws. There's a there's an associativity law, not composition, for flat map. And there are two naturality laws, but the naturality laws do not need to be checked because the parametricity theorem already guarantees that they hold. So this is a significant time savings. As long as the code of flat map is purely functional, which is usually the case, you do not have to check naturality laws. However, proving the parametricity theorem is difficult. So there are two approaches to proving it. One approach is in the papers by Reynolds. You can see the URL here, and Wadler. So Wadler's paper, titled Theorems for Free, explains some examples of how to derive the parametricity property. But the Reynolds-Wadler approach is based on replacing functions by relations. Functions can be seen as relations one-to-one or many-to-one, because you have many different values that must correspond to a single output value of a function. And relations could be many-to-many, so relations are more general than functions. However, it's hard to work with relations. You have to learn new rules about reasoning with relations. And you have to first derive a law with relation variables, which is a difficult concept. Type variable is something that programmers are used to, but relation variables are never used in programming languages. There aren't any such things. Arbitrary relation between types and values. This is a very abstract and difficult concept that you have to learn. But once you derived a law using relation variables, you have to replace them with functions, because actually the naturality law is a law about functions, not relations. So you have to somehow do a lot of work first deriving the relation and then you replace that by function. So it's a lot of work, and it's not obvious how to do that. This replacement is not dictated by the theorem or by any technique. This you have to guess how to replace. So it's kind of difficult to use this approach in order to derive naturality laws. There is an alternative approach which does not use any relations. It's a more direct approach where you directly derive the naturality law, the form of the law. You just write it down, more or less mechanically. There's a recipe for writing it down, and this is based on a technique derived in these papers. And especially in the paper by de Latayade, who proved the parametricity theorem completely in great detail, and analyzed the structure of code for those transformations completely. So this is a very valuable result, but it's unfortunately quite technically difficult. So it's hard to reproduce this proof or follow it. It's a lot of computation and details. So I have developed a different proof in the same vein in this approach, but it is more direct. So this proof is based on profunctors and dinatural transformations. So let's talk about profunctors. Profunctors are similar to bifunctors. They're type constructors with two type parameters. So example of a bifunctor would be this. It is a constructor with two type parameters, and it's covariant in both of these parameters separately. So in the type notation, I write type parameters as superscripts. And so this Scala syntax is written like this in the type notation. So this makes it clear that both A and B are covariant, in a covariant position. Covariant positions are to the right of function arrows or outside of any functions. Contravariant are to the left of a function arrow. So if a type constructor is purely functional, then the type expression is built in completely from products, coproducts, and function types. And so every type parameter must be either in a covariant or a contravariant position. Now, if type parameters are always in covariant positions, then you get a functor in each type parameter. A bifunctor is more than just a functor separately in each type parameter, because the type constructor L must have a method bimap with this type signature. So this method maps both type parameters at once into new type parameters, and this method must have identity and composition laws. So composition law means that if you first bimap with some fg, and then you bimap again with some new functions f prime and g prime, then it's the same as if you bimapped with the composition f and then f prime, g and then g prime. Now this law is a composition that must hold when you transform at once both type parameters with arbitrary functions f and g. So it's stronger than if you just transform one type parameter at a time. Profunctors are type constructors with two type parameters such that the first type parameter is contravariant and the second is covariant. So example is you have a function like this. So x is to the left of the function arrow, and so it's contravariant. Y is to the right of a function arrow, and so it is covariant. Profunctors must have a method xmap, which is similar to the bimap, except that the type of f has reversed direction. And this is because the first type parameter is contravariant. And you must have similarly identity and composition laws for xmap. So a natural question here is to ask if some type constructor is a functor separately in A and B, is it a bifunctor? It's easy to check that A and B have covariant positions. But does it make it a bifunctor? Does it make this law hold, or the laws of identity and composition? And similarly for profunctor. So if we check that A is always in a contravariant position and B is in a covariant position, is that sufficient? Will the laws hold? So the answer is yes, they are always automatically bifunctors, profunctors, and so on, but only if all the liftings in the type parameter A commute with all the liftings in type parameter B. And this is because you can first lift just f as if G is identity, and then you lift just with G as if f is identity. But the composition law for bimap needs to permute the order of lifting. So lifted f, lifted G, lifted f, lifted G must be permuted into lifted f, lifted f, lifted G, lifted G. And that's impossible to permute in general, unless the composition law, commutativity law holds. So these are the commutativity laws, which I will write in more detail here. Here's how we apply the xmap method to some p ab. So let's say p is a profunctor. First you apply xmap with some f and identity. So this only transforms the first type parameter. Then you apply xmap with identity and some g. So that transforms the second type parameter. But you can apply them in the opposite order, like this. And the result must be the same. So this is the commutativity law for profunctors. And we can write it like this. So how do we denote these things? What we need to do is we need to take a type constructor such as this and fix one of the type parameters and consider that as a functor with respect to the other type parameter. So let's fix B, and then this will be a functor with respect to A. In the Scala syntax, using the kind projector, you would write like this. It's a type constructor whose first type parameter is being left free, but the second one is fixed. In the code notation, I write like this, with a bullet for the placeholder of the free type parameter. Now, lifting a function to this functor is denoted like that. And the type of that lifted function would be like this. It transforms the first type parameter from u to v. The second one is held fixed. If we lift with respect to b, fixing a instead, then the lifting will be denoted like that. You lift with respect to this functor whose unknown type parameter is indicated by the bullet, and the type signature of the lifted function is this. The type parameter a is fixed and u is mapped into v. So the commutativity law for bifunctors is written like this. Oh. Can't select. It's written like this. So f and then g is equal to g lifted and then f lifted. So for a profunctor, a very similar thing is done, except that if we fix b, we get a contrafunctor. So this is a contrafunctor in its first parameter, and so we need to lift to the contrafunctor, which is denoted by the down arrow, just to suggest that this is kind of an opposite lifting. And if a function f has the type u to v, the result of lifting is v to u in the first parameter, and the second parameter remains the same. If we fix a instead, then we lift with an up arrow because it's a functor in the second parameter, and the result has this type. So because p has one contravariant parameter and one covariant parameter, it is unambiguous if we just write this. It's clear that this must be lifted with respect to the first type parameter, the second is held fixed. So if we want to write the law more concisely, we can omit these type parameters and write like this. So here I used the notation xmap, but it is quicker to write either this or this. So because of parametricity result, the commutativity laws hold for all purely functional type constructors. So we do not need to verify the laws, the commutativity law and the composition law for bifunctor, as long as it is a purely functional type constructor. So this really is a relief. So this answers these two questions. So yes, these liftings always commute as long as your type constructor is purely functional. And so it is sufficient to check contravariance and covariance. You do not have to check the laws of bimap and laws of xmap. So this is the practical use of parametricity result. That you do not need to check laws. Now, if you're not in the business of checking laws, you won't care about any of this anyway. But people who write libraries like cats, Scala Z, and so on, need to know that laws hold. And also, if you're implementing a new type class, you need to check laws. And so once you start learning about that, you will run into these issues. So it remains to see how we write those laws. So now naturality laws get their name from natural transformations. Natural transformations are functions with type signature of this form, where f and g are functors, or both f and g are contrafunctors. That's another possibility. And the naturality law has this form, which tells us that the lifting commutes with t, except that we have to lift into the different functor. So this is a law that is always of this form. So naturality law always has the same form, but the functors f and g are different for different functions t. So that's why it appears that naturality laws are all different in every case, but it's because this lifting and this lifting has been expanded. It has been written out in terms of a specific f and specific g. So you don't see that this is a lifting to f. You see some code involving f, and you see some other code involving f. But actually, this code is lifting. And many standard methods have the form of natural transformation. For example, pure and head option we already saw. Last option, the same type signature as head option. Reverse, swap for pairs, map, flat map. They have this form. So for example, flat map, which I denote like this, it has this type signature. It has two type parameters, so let's fix one of them. Let's fix A. Then you have this form with functor f defined like this and functor g defined like this. Now, A is a fixed type parameter, so B is the one that we're interested in. So this is a functor because it's B to the right of the arrow under M, and M is a functor. So we know that this is a functor and this is a functor. Now, the naturality law is then written as this equation. Now, this equation doesn't seem to have this form. But if you write it out, if you write out what is the lifting to the functor f, what is the lifting to the functor g, and if you apply this flat map to some arbitrary p of this type and write it out, then you will find that the left-hand side is like this and the right-hand side is like that. See, here is this lifting to m that you already see, but this is not a lifting to g. See, m is this monad here. So first you write this law, and then you write out the specific code for f. So f is this. You write out what is the functor instance for this, functor instance for that, substitute, and you get then the naturality law. And for contrafunctors, here's a diagram. It's the same except the type of f is reversed. So same law, but the type of f must be reversed. So then it's a natural transformation between two contrafunctors. Now, not all methods have type signature that can be in this form. So here are some examples. This method does not have the type signature in this form. You cannot define some f and g so that this is fa and this is ga, and they're either both functors or both contrafunctors. And also for the fold, with respect to b, you cannot define it like this, like fb to gb. With respect to a, you can. This is fa, and this is ga, and ga is covariant in a, because a is behind two layers of arrows. These arrows are curried, so this is a single layer, and this is a second layer. So it is covariant in A, but not in B. So B is neither covariant nor contravariant. It's used both to the right and to the left of an arrow. So no way we can have this form. It's neither a functor nor a contrafunctor. So in order to cover this case, we use profunctors. So we, instead of saying, oh, this must be a functor, we say there must be some profunctor P and some profunctor Q, but these profunctors are being used with the same type parameter. Just we don't see that they're profunctors because they have the same type parameter. So we see a type parameter that is sometimes used covariantly and sometimes used contravariantly, but actually it is because this is what was written. So there were some profunctors that we can easily find. We can just relabel all contravariant positions of B, for example, here. This is a contravariant position of B, and this as well. Call this X. All the covariant positions, this one and this one, call this Y, and you get your QXY, and this is PXY. Now, in this case, it will be just a constant because A is a fixed parameter, but no matter. So this is always possible to relabel type parameters such that any type signature like this has this shape. So this is called a dinatural transformation if it satisfies a naturality law. Now the law is more complicated for dinatural transformation. It has two f's on the left hand side and two f's on the right hand side. But it turns out that all pure functions have a type signature of this form, of the form of a dinatural transformation. And the corresponding naturality law, this law, is guaranteed by parametricity. And so all naturality laws for any type signature are derived in this way. So this is the recipe for writing a naturality law given an arbitrary purely functional type signature. First, you find contrafunctors P and Q so that your type signature has this shape, PAA to QAA, where A is the type parameter that you're selecting. So for instance, here I can select A or I can select B, but in any case I'll have to do the same thing. So it will be PBB into QBB here if I look at the type parameter B. So I can always do that. I can always find P and Q so that it has this form, because I can just take each type parameter, I label it as covariant and contravariant, and I find what P must be and what Q must be. Then I define these liftings, which I showed in previous slides. With respect to P, with respect to Q, there will be specific code involving F, and I evaluate this law with that specific code, and I get something that depends on F and T, and that's the law. So let's look in more detail about this at this law. This law is an equation that should hold. Now this symbol, equality with exclamation mark, I use it for it. This, we know it must hold. This is what it means. Some kind of emphasis of sorts on the equation. So we know that this must hold. This law is an equality between functions of this type. It's a complicated type because now it's no longer coincident or diagonal, as we might say, type parameters. No longer coincident. There must be arbitrary A and B type parameters. Otherwise this law wouldn't work. And both of these functions, when applied to some arbitrary value P of type PBA, must give the same result. So here's how this works. First we map with F. We get PAA because F is a function A to B, and we are contramapping with respect to the first type parameter. So this gets you from B to A here. When we use T with type parameter A, we get QAA, and then we map with respect to parameter A. Now this must be A, not B. This is a mistake. I will correct it in the slides. And the result will be QAB. So the function f has type A to B, so it maps this A to this B. And the lower part of the diagram is similar, except we first map A to B, and then we get T, apply T, we get QBB. Then we contramap with respect to the first type parameter, and it becomes QAB. So this is convoluted, quite complicated law. But it turns out that this is a general form that always works. So this law, if applied to arbitrary type signature in this form, always gives you the correct naturality law. Here's an example. Suppose you have a function filter. Now the filter has this type signature where f is a filterable functor. And the notation could be like this. So how do we derive the naturality law for this function? First, we rewrite it in the form of a natural transformation. But natural transformation cannot work here because this could be FA, this could be GA, but it's not covariant in A here. So we must try dinatural transformation. So let's try dinatural transformation. I mean, I would first try natural if it worked, but it doesn't. So it's simpler with natural transformation, because of a natural transformation, the law is like this. It's a simpler law. So now, okay, simple didn't work. Try more complicated. This is a general law that will always work. So this must be PAA, and this must be QAA. So clearly, this P must be x to 2, so because this is contravariance, and Q must be this. Because this is contravariant, this is covariant. So we call this x, we call this y. So we have defined P and Q. Now we write the code for liftings. So these are all the liftings that are necessary for the law. This is standard. If P is this, a capital P, then the lifting is like this, and so on. And because this does not depend on y, the lifting with respect to the second type parameter is just identity function, and so on. So we derive in a standard way the code for liftings, and we rewrite the naturality law, which could be like this, in the form with specific lifting. So we substitute these liftings into the law. We get this. Now we simplify. So we apply both sides to an arbitrary value of type PBA, which is this. So first we would apply this, we'll simplify, and so on. And finally, what you get is this law. And this is the naturality law of filter. So you see it has more complicated form than just permuting the order of lifting and filtering. Because if you do that, you have to modify the filtering predicate as well. So this F semicolon P is a composition that is necessary in the argument of filter. it follows mechanically from the general naturality law of dinatural transformations. If you just expand all the functions, substitute the specific lifting code for the specific functors P and Q, and then you derive the law. So there's no guessing. This procedure can be made automatic. It can be made mechanical by algorithm, if you wish. So now I talk about the last result, which is the uniqueness of functor implementations. Functor implementations are the implementations of fmap method for a specific type constructor. So these are the two statements or theorems that follow from parametricity. If you have a purely functional type constructor, which is covariant in A, then there is a unique purely functional implementation of fmap that satisfies the laws. And if you have the type constructor that's contravariant in A, then there is a unique implementation of contramap or cmap, which has this type signature. So note that many type classes might admit several non-equivalent implementations of a type class instance, even for the same type constructor. So for example, filterable, monad, and applicative, you can have different applicative or filterable or monad instances for the same type constructor. It is well known, for instance, that list has different applicative instances, or filterable instances also can be different. But not so for functor. Functor and contrafunctor instances are unique. There cannot be non-equivalent implementations if laws are satisfied. Now here, they're all law satisfying or law abiding, all these non-equivalent instances, they're all lawful. So you need to choose between them based on your business logic or requirements. But here there is no choice. So these are the theorems that there's no choice. Now, in the remaining part of my tutorial, I will show proofs of these statements. So I have shown you 4 results. I will show proofs for some of them. The easiest proof is that of uniqueness of functor implementations. It assumes parametricity. So here's the proof. I will only prove statement 1 because statement 2 is quite similar. So given a functor f, first of all, we always can construct the standard code of fmap, which is the code that's involved in the naturality laws. Something like what I was showing here. So this is this example of a standard code, which is derived mechanically from the type constructor, or this one. It's code that could be derived mechanically. So that's the standard map. Now suppose there exists another implementation, fmap prime, which is lawful and purely functional, but different, possibly different. And we need to show that they're actually not different, they're the same. So how do we show that? Well, this fmap prime, it must have this type signature, and the code must be something like this. So it has a naturality law with respect to b, the type parameter b. And this naturality law is of this form. So this can be derived from parametricity or from the natural transformation, this form of type signature. So It's the type signature of functor with respect to B going to a functor with respect to B. So then if you write out the liftings and apply to some f with some arbitrary g, then you have this. So this is a naturality law. Note that this naturality law involves the lifting of g, and this lifting is the standard one. It is the f map without the prime. Why is that? A very important point in the proof. This is because the parametricity theorem that derives that the naturality law holds depends on those standard f maps. The proof of the parametricity theorem directly uses the code of the standard f map. I will show in some way how that works later. But this is an important point. So this naturality law involves the standard f map together with f map prime. So now we can transform this equation in the following way. First, we use the composition law for f map prime, which we assume holds. So now this gives us this. It should still be equal to that. Now, functions f and g are arbitrary, so let's just choose parameters a and b the same and f to be identity function. So then we have this equation. Now this is equal to identity, so we can omit it. And this is also equal to identity. So I'm just rewriting this here with f equals identity, and this with f equals identity. So, as I said, the lifting of g is the standard lifting, because that is what the parametricity theorem proved, that naturality law holds with respect to the standard lifting. Now we have an equation that f map prime of g equals f map of g. Now this must hold for arbitrary g, and this is the same as to say that the function f map prime and f map are the same function. Now, the proofs of commutativity law for profunctors and the proof of parametricity theorem are quite complicated and long, so I'm not going to go through them in all detail. I will show the plan of the proof and a little bit of detail. So the proof that I came up with for parametricity theorem actually depends on the commutativity law for profunctors. So let's prove that first. So the main idea of proof is to go by induction on the type expression of the of the profunctor P. If this profunctor is purely functional, which is what we assume, it must be a combination of unit type. So what types do we get out of purely functional code constructions? Well, we have tuples, we have coproducts or disjunctive types, we have function types, we have unit. That's all. And we have recursive applications. So it means that for any purely functional program, the type must be a combination of unit type, then type parameters, of course, then some products, some coproducts, or disjunctions, as I call them, and exponentials or function types. And also we can have type recursion, so you can use the type P in its own definition. And that's it. There are no other options for the type. It cannot be some type from a library, some class defined in some Java library, none of that. That is not allowed in the purely functional code. So that's the price we pay for the so-called free theorems. So for each of these cases, we need to show that the commutativity law holds, and induction allows us to assume that the commutativity law already holds for sub-expressions. So for example, if it already holds for some p and q, then we must show it also holds for these, and for these profunctors. Now note reversing of the type parameters, which is important. Because here x must be contravariant and it's behind an arrow. And also we need to show that the commutativity law holds for profunctors p defined recursively using this equation, where S is some kind of structure, functor, or constructor that must be contravariant in X but covariant in Y and R. So R is this recursive instance of the type. It must be covariant in that. So for this type constructor, we can again use induction assumption that the commutativity law holds for it with respect to any of the type parameter pairs. And then we must show that the commutativity law holds for P. And we need to use the code of the liftings of instances of functor, of contrafunctor, for products, co-products, exponentials, and recursive types. So for example, if I know how to lift to P, and if I know how to lift to Q, then I know how to lift to this profunctor. And this is the standard lifting code that I was talking about. So we need to use that code, and then we need to prove this induction step. And the base case is easy. Just prove that the law holds for these trivial profunctors. So here's an example. For the product, let's say R is a product, then the lifting to R is defined using this code. So this is the standard lifting code. If these are standard lifting codes for P and Q, and so on. So this is recursive in the proof. So the proof is inductive, and it decomposes the type expression of P through co-products, products, and exponentials until you go back to all the way down to unit types and type parameters. So that's all you're allowed to use. So that's how the proof goes, and it can be done. So this proof works, and you just have 1, 2, 3, 4 induction steps and 2 base cases. To prove the parametricity theorem itself, what we prove is that there's a naturality law for a dinatural transformation. And the naturality law, which is this complicated law that I was showing here, holds for any transformation whose code is of this form, where P is this argument and expression, expr, is some code that has type QAA, and this code must be built up from the 9 allowed code constructions. So the main idea is that we go by induction on the code of this expression, of the body of the function. So we assume that any sub-expressions already have the law. So for any function whose body is a sub-expression of this, already has it's already dinatural, already proved that. So that's the induction assumption. The base cases would be unit and using the bound variable, using an argument p, so p to p, for example, identity function. So we have to prove the law for unit here and for identity function. And that, if you write it out, is exactly the commutativity law for the profunctor P. So that's how the base steps are proved. And the induction steps, for example, for code construction 3, so 1 and 2 are base cases. Code construction 3 is create function. So it means that the code of T is this. So expression expr is a nameless function, is z to r, where z is some profunctor, r is some profunctor, so q is a function type. The inductive assumption is that any function with body r satisfies the law. So let's take p times z instead of this x. And so the inductive assumption is that for any function u of this kind, so we have a function p times z going to r. So r is this expression that was here. Its type is this now. For any function of this type, the naturality law already holds. So we can write down what that law is, given the types, and derive the law for t. So t is then defined like this, and we can write down the law for t, substitute these liftings, and directly calculate that this law holds. So this is how the proof goes for step 3. Now there are 3 and so on 9, and so there are 7 inductive steps and 2 base cases. And actually in 2 of the 7 inductive steps there are technical difficulties. They don't go through so easily because they involve composition of dinatural transformations, and they do not generally compose. Natural transformations compose. This is easy to show. If you have natural transformations, FA to GA and GA to HA, you can compose them, and these 2 laws compose. So it's enough to know that the laws hold for natural transformations, say T and U, and then the composition of T and U is again natural. But this is not true for dinatural transformations. It's not enough to know that F and G are dinatural, even though the types match. F composition with G is not automatically dinatural. It does not follow just from the laws of the 2 dinatural transformations. So this is a technical difficulty, but there are tricks to overcome this difficulty. The statement is still true, and dinatural transformations that are obtained from purely functional code, they compose. They always compose. It's not just, it's a technical difficulty that can be overcome. Although I'm not fully satisfied with the way I did it. But let me summarize. So purely functional code is a restriction on how we write programs, and this restriction enables a lot of mathematical reasoning about code. So in this tutorial, I talked about specific kinds of reasoning that have to do with naturality laws. There are also other things that you can do with purely functional code. For example, type inference or code inference. You can prove that certain type signatures have specific implementations, or you can prove that one code is equal to another by computation. So this is this is not in this tutorial. I did it in other tutorials. Here I'm talking about naturality laws. So once we restrict to purely functional code, we get a lot of benefits. Any type constructor now will have the form of a diagonal profunctor, or profunctor whose type parameters are chosen to be the same. So if we're given some type constructor, we can derive what P must be. Functor, contrafunctor, and profunctor instances are unique. So we can derive uniquely what the xmap function must be, what the fmap function must be, and so on. Any purely functional code obeys a naturality law, so we don't need to check them. Bifunctors and profunctors obey commutativity laws, that we don't need to check them. So as long as we have the type constructor that has a purely functional form, we derive everything. We mechanically derive unique and lawful functor, bifunctor, profunctor, contrafunctor instances, and we know that the laws will hold, and we know we don't have to check them. So I have shown how this could be proved in a very direct way by induction on the allowed kinds of code. The full details and the proofs are in the book that I'm writing in Appendix D, and the full source for this book, which is free in the sense of the GNU Software Foundation, Free Software Foundation, is here on GitHub.